Alright, so in today's tutorial video, I want to look at statistical methods for analyzing one sample data in Stata. And before we proceed, I'll urge you to kindly take a look at my previous tutorial video on the flowchart for classifying data, okay? Because in that video tutorial, I have explained and illustrated the data structure for one sample data, which will help you to catch up with everything that I'm going to do in today's tutorial video. Okay, so now let's get started. Generally, anytime you have one sample data, there are two statistical methods or techniques you can actually use to analyze such a data. We have the parametric test and we also have the non-parametric test. Parametric tests are statistical tests for population parameters such as the mean, that is based on the assumption that the population from which the samples are selected will follow a normal distribution. The non-parametric test, on the other hand, are statistical tests for population parameters such as the median, that is not based on the assumption that the population from where the samples are selected will follow a normal distribution. So the type of parametric test that we often use in analyzing one sample data is called the t-test or the one sample t-test. And the type of non-parametric test we often use in analyzing one sample data is called the sign test or the quantile test. Let's take a look at the parametric test for one sample data, which is the one sample t-test. So the one sample t-test is a statistical hypothesis test used to determine whether an unknown population mean is different from a specific value. For example, we might want to know if the mean waiting time in a doctor's office is greater than 1 hour, or if the mean growth of roses is 4 inches or more after 2 weeks of treatment with a certain fertilizer. There are some assumptions which must be satisfied before we make use of this test. One of the assumptions is that the data must be continuous. The other one is that data must be normally distributed, okay? Let's take a look at a non-parametric test for one sample data, which is the sign or the quantile test. The sign test is a statistical hypothesis test used to determine whether an unknown population median is different from a specific value. For example, we might want to know if the median waiting time in a doctor's office is greater than 1 hour, or if the median growth of roses is 4 inches or more after 2 weeks of treatment with a certain fertilizer. There are some conditions which must be satisfied before we also make use of this test. One of the conditions is that the data must be continuous, and the other one is that data must not be normally distributed, okay? So now let's take an example. Using the iris dataset as a researcher, you wish to test whether the average length of the sepal from the iris dataset is different from 6 centimeters. Perform statistical analysis for this data. Okay, so before we do this in Stata, let's take a look at the iris dataset in a CSV format. So this is the iris dataset, right? And this is a clean data. I'm going to leave this data file in the description of the video so that you can download it. Now, before you analyze any data, you first of all have to prepare or clean it. So we have assumed we have passed through the data cleaning or data preparation stage. So we are just going to even just adopt some one or two data manipulation, start with our analysis. Okay, so this is the iris data set, and basically we want to find out if the average length of the sepal, which is this variable, right, is different from 6 centimeters. Now if you just make use of this um, values of the variable in your analysis in performing either the t-test or the quantile test, you may end up providing a wrong inference, because you have to note that the sepal length um, is coming from three groups of the species. We have one for Setosa, we also have one for versicolor, and we also have one for virginica. So before you start with your analysis, you have to first of all filter the sepal length, right? For Setosa, you also have to do same for versicolor and do same for virginica, and then maybe based on the information you obtain from your exploratory data analysis, you may decide to go with either the sign test or the quantile test, okay? So that's basically what you're going to do. So now let's quickly jump into our Stata. So this is my Stata window, right? And I have a do file here. I'm going to make use of a do file instead of using the drop down menu. Okay, so you can get a do file by clicking on this icon here, right? Once you click on this, you can get a do file, and make sure that you save it in the folder where you have your um, data file. Okay, So now the first thing that we want to do is to basically set working directory. Okay, so in order to set a working directory, we need a function cd. Okay, then you copy the path where you have your data file and your do file. Okay, so let me show you how you can get this. So let me go get you the folder where I have my data file and the do file. So this is my do file, this is my data file. So I just have to click here, right, and copy this path. Okay, so once you copy, you can go back to your Stata window or your do file, right, and just paste it in this double quote. Okay, make sure that you paste in double quote and don't leave any space in here. Okay, don't leave any space. Make sure that the space are closed. So once we do this, we can set our working directory. Okay, so I'm going to execute this by using Control D, or basically you can use this icon to execute it. So I'm going to use a shortcut Control D. Okay, so now let's check the effect from our result window. Alright, so we are now good to go. Once we have done this, we can proceed and try and import the data set. So because it's a CSV format, I'm going to use the function import. um, Let me highlight this. I'm going to use the import delimited, right? Then the name of the data comes, which should be in double quote, clean data.csv. Then we want to clear if there's any previous existing data set in the memory. In the Stata memory, I want to clear it because Stata doesn't work with multiple data sets at the same time. So we want to clear any previous data set in the memory so that we can make use of this current one that we are importing. So let's quickly execute this. Control D. Let's see the effect in our result window. So it's still compiling. Alright, so I think it's done now. We have 5 variables and 148 observations. So how do we get to view our data set? We are going to make use of the browse function. Okay, so let me highlight this browse function. So I'm going to execute this. Okay, Control D. Alright, so this basically displays the data set in a spreadsheet form like the one we saw in this CSV format, okay, the Excel format. So I think, oh sorry, let me close this. Okay, so I think we are good to go now. Let's go back to the do file and try to get more information with regards to the data set. So the next thing that I want to do now is to basically um, get a structure of the data set. Okay, so we're going to use the describe function to get that. So Control D. Let's check the effect in our results window. Alright, so we have 148 observations, we have 5 variables, and if you scroll down, what do we see? We have the data type for the variables. Okay, let me scroll down a little bit. So you can see that we have the separ length, separ width, petal length, and petal width. They are all float, right? Which basically means they are numeric, and species is string. Okay, but we know that if you are dealing with string in your analysis, you may have some challenges. So in our data manipulation, we are going to encode this by assigning values to the labels of the species. Okay, so let's quickly do that. So in our data manipulation, we first of all want to convert the string variable into numeric by basically assigning values to the labels. But first of all, let's use a code book to get some more detailed information with regard to the species variable. Okay, so let's execute this. Control D. Alright, so you can see that the type is string, and if you look at the frequency for the values, you can see that these are all string, right? So basically we want to assign some values to the labels of these species. Okay, so let's go back to our do file. So I'm going to make use of the encode function, right? So I'm saying that we're going to encode the species. Okay, then we don't want to override the previous species. We want to get a new name for this transformation. So we want to say species 1 should be the name for the variable that would have the effect of this and transformation. Okay, so let's execute this. Control D. Now let's use the describe function to see the effect. Control D. Okay, so let's look at it now. Now you can see that we have added another variable to our data set, which is the species one. By this time the data type is long, which is basically numeric. We have basically encode this previous one by assigning values to the labels. So you can also use the codebook to get more detailed information with regards to the effect. So control D. Alright, so you can see now that we have assigned values to the labels of the species, which is now quite good for us to make use of. So we can drop the previous species, right? So let me highlight this and drop that. Then we can use the describe function to see the effect. Control D. Let's go back. So we see now we have dropped that previous one. So we now have the one that we have transformed, the encoded one, species one. So let's go back. We may want to even rename our variables if we wish to. So let me highlight this once. So we are going to rename the sepal length as SL, sepal width as SW, petal length as PL, petal width as PW, and species 1 as SP. Okay, so let's execute this. Control D. Then let's use the describe function to see the effect. So Control D. Alright, so you can see now we have changed or renamed the variables. Okay, so I think we are good to go. Now the next thing is to filter our data set, right? We are supposed to filter the sepal length. sorry. We are supposed to we are supposed to, I think I'm having some challenge with my voice. We are basically supposed to filter the sepal length for each of the labels of the species. Okay, but in Stata it's very difficult to work with multiple data set at the same time. So basically what we are going to do is that we are going to embed the data filtering right in our analysis. Okay, so we are going to start with exploratory data analysis, which is very important because through the exploratory data analysis we are going to get to know whether we are going to make use of the sign test or the quantile test. It is from this analysis that we get to know whether we are going to make use of a particular kind of test. Okay, so it's very important we pay close attention to exploratory data analysis. Now if you have not watched my previous tutorial video on UDA in Stata, I'll urge you to take a look at that if you want to maybe get some more information with regards to that. Okay, so now let's scroll down and start with our UDA. Alright, so in our exploratory data analysis, basically what we're going to do is to start with the summary statistics for the various labels of the species. So we want to get the summary statistics of the sepal length for Setosa. So I'm going to use a summarize function, right? So I'm going to say summarize sepal length if the species, so yeah, I'm trying to include a data filtering in my analysis. If the species is equal to 1, yeah, the double equality sign is being used to basically show that we are interested in the Setosa. Remember that in our data encoding, 1 was assigned to Setosa, 2 was assigned to vesicular, and 3 was assigned to virginica. So using this condition means that we are interested in only that of the Setosa of the sepal. So let me show you this using um, the data editor. So this is basically what it means. Once I specify the species to be one of the sepal length, it's going to basically highlight this once, right? It's going to pick these values. I think it earns here, yes. So from 1 to 49, these are all Setosa, right? Then once I change the species to 2 of the sepal length, it's going to pick values from here. That's the 50th observation starting from vesicular. Then it will pick those ones up to, let's say, I think it ends here 99, yeah, observation row 99. So these are all vesicular. Then once I change the SP to 3, it's going to start for virginica. that is the 100th observation, pick these values and perform the analysis on it. Okay, that's basically what it's going to do. So let's go back to our do file. So I want to get a summary statistics, right, of the sepal length for Setosa. So let's execute this, Control D. Alright, so here we go. So we can see some summary statistics. We have 49 observations. We also have the mean value to be around 5 centimeters. This is where most of the data points are being clustered. Okay, the peak of the data set is around 5 centimeters. We also have information with regards to the variability in the data set, which is given by the standard deviation and variance. Variance is measured in square unit, whilst the standard deviation is measured in linear units. So it's always good to interpret that of the standard deviation. So if you are to look at the distance of each data point from the mean, it is around 0.34 centimeter, which is quite low. So this is quite good. We also have information with regards to the skewness and kurtosis. Okay, so the skewness basically describes the degree and direction of departure from symmetry, and we know that a distribution is said to be symmetric if it has the same shape on either side of the center value. Okay, so once we have a distribution having an equal shape on either side of the center value, then we have a skewed distribution. Okay, so looking at this from literature, if the skewness coefficient is within the range of minus 0.5 and plus 0.5, then we can say that the distribution is nearly symmetric. So looking at this, we can say that the distribution of the Setosa, right, the distribution of the sepal length for Setosa is symmetric. Looking at this coefficient, which falls within the range. Okay, but if the skewness coefficient is, let's say, greater than +1 or less than -1, then we can say it's highly skewed. Okay, now in terms of kurtosis, we often make use of the SS kurtosis, which is basically used to the SS kurtosis is basically used in comparing the kurtosis coefficient with that of the normal distribution. Okay, and it is obtained by subtracting 3 from this kurtosis coefficient, or basically you can compare this to 3. Once the kurtosis coefficient is close to 3, we can say that we have a mesokurtic distribution, which means that the thickness in a curve is normal in shape. Kurtosis basically describe the thickness in a curve, or let's say how heavy or light the tails of the distribution will look like. So once the kurtosis is close to 3, we know that we have a mesokurtic distribution, and if the kurtosis is less than 3, then we have a platykurtic distribution, which means that the thickness in a curve is flat and spread out. Okay, or the tails of the distribution seems to be flat and spread out. And once the kurtosis is greater than 3, then we know that we have a leptokurtic distribution, which means that the thickness in the curve is um, high and thin, or the tails of the distribution seems to be high and thin. Okay, so with this coefficient, we know that we have a platykurtic sort of distribution. We also have information with regards to the percentiles, but in most cases, we often choose to interpret that of the 25th percentile, the 50th percentile, and the 75th percentile. The 50th percentile is the same as the median, which means that if you are to divide our data set into two equal parts, right, we have 50% of the values falling below 5 centimeters and 50% of the values will be about 5 centimeters. With the 75th percentile, it is the same as the third quartile. Okay, so we know that 25% of the values are about 5.2 centimeters and 75% of the values fall below 5.2 centimeters. So we can even interpret this as the top 25% of the sepal from the Setosa plant increases in length than 5.2 centimeters. And with the 25th percentile, it is the same as the first quartile. Okay, so we know that 25% of the values fall below 4.8 centimeters and 75% of the values fall above 4.8 centimeters. So we can also interpret this as a single Setosa plant of the sepal chosen at random has a 75% chance of increasing in length than 4.8 centimeters. So these are some of the descriptive summaries you can basically talk about before you even start with your main analysis. from these descriptive summaries, we get to know that the shape of the distribution, right, of the sepal length for setosa is symmetric. So this is basically informing us that we can make use of the parametric kind of test. Okay, so it's very important we start with this kind of analysis. Let's go back to our do file and look at the summary statistics of the sepal length for versicolor. So this time, let me highlight this. Okay. Okay, so now I want to look at the summary statistics of the sepal length for setosa. So summarize sepal length if SP is equal to 2. Okay, then I'm using the detail function to get more summary statistics information. So let's execute this, Control D. So here we go. We have that of 50th. We have 50 observations, right, for the sepal length for versicolor. We have the mean value getting close to 6 centimeters. We also have information with regards to the variability in the data set. And if you look at the skewness coefficient, it's within the range of minus 0.5 and plus 0.5. So we can also say that the shape of the distribution, right, of the sepal length for setosa is approximately symmetric. So yeah. Then if you look at the ketosis coefficient, it's also less than 3. So we can say that we have a plateautic sort of distribution, which means that the peakness in the curve is flat and spread out. Okay, let's check that of the summary statistics of the sepal length for Virginica. So I'm going to highlight this, right? So let's execute this, Control D. Alright, so we can see that in here we have 49 observations. The mean is 6.60 centimeters. We also have the skewness coefficient getting close to 0, so this is also a sort of symmetric distribution. And if you look at the ketosis, it's close to 3 at the same time, less than 3, so we have a kind of plateautic at the same time mesochatic kind of distribution. Okay, so aside using this kind of numerical summaries, we also want to use other important exploratory information like the box plot to get more detailed information. So the box plot, aside helping us with a 5-number summary, the box plot also help us to get a shape of the distribution, right, in terms of checking for skewness. Okay, so let's visualize the 5-number summary by making use of the box plot. And we want to start with a box plot of the sepal length for setosa. So let me highlight this. Okay, so graph box of sepal length if the species is equal to 1. Then we want to give a title box plot of the sepal length for setosa. So let's execute this, Control D. Okay, so I'm expecting a window, a graphic window. It's still compiling. One is that we are going to see that. Alright, so here we go. So let me maximize this. Alright, so I can change the orientation of this plot. Let me click on the graphic editor. So click on this and double click on this graph. So let me change the orientation to horizontal and click on apply and okay. So once I change the orientation, I don't see the extreme values. Okay, so with the box plot, the first item in the box plot is shown in here. This is basically pointing towards the minimum value. The second item is indicated here, which is pointing towards the first quartile or the 25th percentile. This middle line is pointing towards the median value or the 50th percentile, and this is pointing towards the third quartile or the 75th percentile. And we also have the last item, the 5-number summary, pointing towards the maximum value. Okay, so aside getting information with regards to the 5-number summary, the box plot also helps us to get a shape of the distribution. Now in terms of skewness, if you are to use this box here, this middle box as the center line, then it means that we are looking at the distance from the minimum value to the first quartile and also compare the distance from the maximum value to the third quartile. We can see that they are almost, this box seems to be in the middle, right? Comparing the distance, so we can say that this distribution is nearly symmetric. Also, if you have to compare the area at the upper half of the median, it's almost the same as the area at the lower half of the median. So looking at this, we can say that the distribution of the sepal length for setosa is nearly symmetric. Okay, so let me close this. I don't want to save this, so let me close down save, and let's go back to our do file. Alright, so let's get that of the box plot of the sepal length for vesicular. So let me highlight this. Okay, so now I want to get a box plot of the sepal length for vesicular. So let's execute this. Alright, so in here, if you had to use this box as the middle line, you can see the distance from the maximum value to the third quartile is almost the same as the distance from the minimum value to the first quartile. Okay, even though the area at the upper half of the median seems to be a little bit larger compared to the area at the lower half of the median. So we can also say that the distribution of the sepal length for vesicular is approximately symmetric. Okay, so let me minimize this and go back to the do file. Let's highlight this to get a box plot of the sepal length for vaginica. Okay, so this time let's execute this. Control D. Alright, so in here we can see that we have some extreme values. Having extreme values does not necessarily mean that they are outliers. I've already explained this. You can watch my previous tutorial video on GDA in Stata. Okay, so you have to be very careful when you're dealing with outliers. So looking at the shape of the distribution, the distance from the minimum value to the first quartile is almost the same as the distance from the maximum value to the third quartile, even though the area at the upper half of the median seems to be larger than the area at the lower half of the median. So looking at this, we can also say that the distribution of the sepal length for Virginica is symmetric. Okay, so let's go back to the do file. So aside, you see that the box plot helps us to get information with the 5-member summary, at the same time get to know the shape of the distribution in terms of checking for skewness. Now, how do you check for ketosis also? In order to check for ketosis, let's make use of the histogram plot so that we can include the kernel density estimate within it so that we can check for the spread, how heavy or light the taste of the distribution will look like. Okay, so let me scroll down and let's get a histogram plot of the sepal length for setosa. So I'm using the hist function. Hist, that's the histogram of sepal length if the species is equal to 1, that is for setosa. And here I'm including the kernel density estimate, which will basically draw the help us to estimate the density, probability density function for the setosa variable within the histogram plot. Okay, and then basically I'm going to draw the histogram. The title is histogram plot of the sepal length for setosa. Okay, so let's try and execute this. Control D. Alright, so if you look at this histogram plot of the sepal length for setosa, this is a kernel density estimate, which is basically trying to estimate the probability density function for this data. So you can see that looking at the taste of the distribution, we can see that this is flat and spread out. So that's why from the numerical summary we saw that the ketosis coefficient was less than 3, and we were able to conclude that it's a sort of plateaued type of distribution. And the graph from the histogram plot with a kernel density estimate, we can conclude that the distribution, right, of the sepal length for setosa is plateaued. Okay, let's go back to our do file and check that of the histogram plot of the sepal length for versicolor. So let me highlight this. Sorry, let me highlight this. Okay, so this one is giving us the box plot of the sepal length for versicolor. Okay, so let's execute. Alright, so we can see, I think wrong code of line. I'm supposed to highlight this instead. Okay, so let me highlight it. This one is giving us a histogram plot of the sepal length for versicolor. Okay, alright, so let me pull it to the right side. Okay, alright, so now let's execute this. Control D. Alright, so if you look at the kernel density estimate, you can see that this is a sort of plateautic sort of distribution, right? You can see that the taste of the distribution is not normal in shape but seems to be flat and spread out. Okay, now let's check that of um, the histogram plot of the sepal length for Virginica. Okay, so hist of SL if SP is equal to 3 kernel density estimate, then we give a title to it. Okay, so let's execute this. Alright, so from the left hand side getting to the middle value, you can see that the tail, the kernel density estimate seems to be normal in shape, but heading from the center value to the right hand side, we can see that it seems to be flat and spread out. So that was why we were in between whether it was plateautic or mesochaotic. But looking at this graph, we can say that the distribution of the sepal length for Virginica is plateautic. Okay, because the taste of the distribution seems to be flat and spread out. Okay, alright, so I think we are good to go. So the information that we have obtained so far from the exploratory analysis is basically indicating that the distribution of the sepal length for Setosa, for vesicle and for Virginica, they are symmetric. So from this we can basically know that we are good to make use of the parametric kind of test, which is the one sample t-test. But before we start with that kind of test, we have to test for the assumption. Already the data is continuous. If you look at this, you can see that there's variables. The data points are already continuous, so we don't want to worry ourselves much with this. What is most important is to check for the normality test, right? To ensure that it satisfies the normality assumption. So even though from the exploratory data analysis we can confirm that the distribution is symmetric, let's test for that assumption before we start with the t-test or the quantile test. Okay, so let me scroll down. So in using the testing for the normality, we want to start with a quantile QQ-Plot, which is one of the most frequent used tests to check for normality. The quantile plot or the QQ-Plot basically draws the correlation between a given sample and the normal distribution such that if the data is approximately normal, then the plot will closely resemble a straight line sloping upward to the right. Okay, so let's check that of the QQ plot of the sepal length for Setosa. So I'm going to highlight this. Okay, so the Kinome function that is going to help us to get a QQ plot. So of sepal length if the species is equal to 1. Okay, so we are interested in that of Setosa. So let's execute this. Control D. Okay, so we can see that in this plot, the points, these are the data points, they are almost on the line, right? And they are sloping upward to the right. So this is an indication that the data of the sepal length for Setosa is normally distributed, and therefore making use of the t-test is required. Okay, let's check that of the QQ plot of the sepal length for versicolor. So let me highlight this. Okay, so let's execute this. You can see that in here the points are also on the straight line and they are sloping upward to the right. Okay, so this is an indication that the data of the sepal length for versicolor is normally distributed, and then for making use of the t-test is also required. Let's go back to our do file and check that of the QQ-plot of the sepal length for Virginica. So let me highlight this. Okay, so let's execute this. We can see that some of the points seems to deviate from the straight line, like just one of the points and some few points, but we can see that majority of the points are on the straight line sloping upward to the right. So we can also say that the data of the sepal length for Virginica is normally distributed, and therefore making use of the t-test is required. Okay, so sometimes you see with some of the plots you may be confused whether the plot is um, satisfying the normality test or not. So sometimes we don't rely on just one test. We can also rely on other tests like the Shapiro-Wilk test. Okay, this tests the null hypothesis that the data is normally distributed. Okay, so we don't just sorry for that. We don't just rely on one test. We can also rely on other tests. We also have the Anderson-Dalen test, which is a modification of the Kolmogorov-Sinov test, but let's stick to the Shapiro-Wilk test, which has the null hypothesis stating that data is normally distributed. Okay, so let's use the second test to confirm the QQ plot. So let's get that of the Shapiro-Wilk test of the sepal length for setosa. So we are going to make use of this function as a work sepal length if sp is equal to 1, meaning we are interested in that of the setosa variables, okay, or the test. So let's quickly execute this. Control D. Alright, so here we go. So we can see that if you check this, you can see that we are interested in the p-value, right? Not the test statistic or the observations. We are interested in the p-value. So I want to compare this p-value to the alpha level of significance or the threshold level of significance at 1% or 5%. We only reject the null hypothesis if this p-value is less than or equal to the alpha level of significance at 1% or 5%. So because this p-value, right, is greater than the alpha level at 1% or 5%, it means that we are failing to reject the null hypothesis and conclude that the data of the sepal length, right, for setosa is normally distributed, and therefore making use of the t-test is required. So this is basically confirming to the information we had under the QQ plot. Okay, let's check that of um, the Shapiro-Wilk test of the sepal length for versicolor. So let me highlight this, execute Control D. Alright, so this is for versicolor. If you look at the probability value or the p-value, this observed level of significance is basically greater than the threshold or the alpha level of significance at 1% or 5%. So it means that we are failing to reject the null hypothesis and conclude that the data of the sepal length for versicolor is normally distributed, and therefore making use of the t-test is required. Let's do that for Virginica. So Shapiro-Wilk test for Virginica. So let's execute Control D. Alright, so we can see that the p-value is also greater than the threshold value or the alpha level of significance at 1% or 5%. So we are failing to reject the null hypothesis and conclude that the data of the sepal length for Virginica is normally distributed. Okay, so making use of the t-test is required. Okay, so from here we are good to go. So we can now confirm that the distribution of the data, right, or the distribution of the sepal length for setosa, for versicolor, and for Virginica, they all satisfy the normality assumption. So we are good to make use of the parametric test or the one sample t-test. So now let's scroll down. So I want to start with let me scroll down. Alright, so in here The null hypothesis is that the null hypothesis is that the average or the mean value of the suppellant is 6 centimeters, and the alternative hypothesis is that the average or the mean value of the suppellant is different from 6 centimeters. That is the alternative hypothesis. So I want to start with the one sample t-test with suppellant for Stata. So let me highlight this. So we are going to say t-test suppellant is equal to this is the hypothesized value, right, if the species is equal to 1. But before we execute this, let me clarify this, that in most books we come across the case that the t-test can only be used, or it can be used when, that's one of the conditions, it can be used when the sample size is less than 30, apart from the fact that if the data is coming from a population that is somewhat distributed. One of the conditions also states that the t-test can be used when the sample size is less than 30. So we know that when the sample size is more than 30, we make use of the z-test, right? But one thing that you have to note is that the t-test is also a symmetric distribution, which is basically a family of curves based on the concept of degrees of freedom, okay? And this is related to the sample size. So as the sample size increases, the t-distribution approaches the standard normal distribution. So even if you have a sample size that is more than 30 in practice, you can still make use of the t-test and you still be doing the right thing at the end of the day, okay? So we can now execute this. So t-test of the sepal length, so we have to use the hypothesis value, which is equal to 6 if we are interested in that of the sepal length for Stata. So let's execute this, Control D. Let's check the result window. Alright, so the mean value of the sepal length for Stata is 5.02 centimeters. We want to find out if this mean value is different from this or it is due to chance. Now, if you look at the p-value, we have p-value for the left t-test, we have p-value for two t-test, and we have p-value for right t-test. We are interested in this one, the two t-test. If you look at this one, the p-value is 0.000, right? If you have to compare this p-value to the alpha level of significance at 1% or 5%, it means that we are basically going to reject the null hypothesis and conclude that the average value or the mean value of the sepal length for Stata is different from 6 centimeters, okay? So that is the conclusion that we can draw based on this information. Let's go back to the do file and check that of the t-test, one sample t-test of the sepal length for, sorry, let me change this to scientist. Oh, sorry. Um, let's check now the one sample test of the sepal length for vesicular. So let's try and execute this. So now I'm interested in vesicular, so I'm changing this to 2, right? So let's execute this, Control D. Alright, so the mean value is almost getting closer to 6 centimeters. We want to find out if this mean value is different from the hypothesis value or it is due to chance. If you look at the result from the p-value for the 2T test is 0.3849, and this is greater than the alpha level or the threshold level at 1% or 5%. So it means that we are failing to reject the null hypothesis and conclude that the mean value of the sepal length for vesicular, right, is not different from 6 centimeters. Okay, so that's the conclusion that we can draw. Then let's check that of the one sample test of the sepal length for Virginica. Okay, so let's execute this, Control D. Alright, so the mean value is 6.60 centimeters. We want to find out if this mean value of the sepal length for Virginica is different from the hypothesized mean, which is 6 centimeters. And if you look at the result from the 2T test, we have 0, the p-value is 0.000. If you have to compare this to the alpha level at 1% or 5%, it means that we are going to reject the null hypothesis and conclude that there's enough evidence to indicate that the mean value of the sepal length for Virginica is different from 6 centimeters. Okay, so that is the conclusion that we are going to draw. Now, suppose the assumption that we check for normality, right, failed. Suppose the normality assumption failed for the distribution, right, then it means that you are going to resort to the non-parametric test and make use of the quantile or the sign test. Okay, so assuming the assumption, right, failed, then we are going to proceed to that of the non-parametric test. So let's scroll down. Now, with a non-parametric test, one thing that we have to note is that it is used to take the value of a median, right, for a specific sample. So before we can work with the sign test, we have to first of all generate a variable, right, for median, where each of the data point is made up of the hypothesized median value. Okay, so that's basically why I want to generate a variable for median. So let's do that. So I'm using the generate function to basically generate a new variable, right, and each of the data points is going to be made up of the hypothesis value, that's 6 centimeters. Then we can add a label, right. We want to label this as median variable, even though the name that I'm assigning it to is mdvar. Okay, so let's execute this, control D. Then we can use a describe function to see the effect. Okay, so now let me use the data editor to show you the effect. Okay, so now we have created a median variable, right, where each of the data point is made up of the hypothesized value. Okay, the reason for doing this is that we are basically going to compare each of these data points of the sepal length to that of the this median value. Okay, and what you're going to do is that if this data point is greater than this median variable, we are going to assign it as a positive sign. Then if this is basically if this data point is less than this median variable, we are going to assign it as a minus sign. If this data point is equal to this median variable, then basically we are going to discard it or assign it as 0. Okay, and then this is done so that if the null hypothesis is true, then the probability that a sample value results in either a plus or minus sign, right, is going to be equal to 0.5, right, which implies that the sample or the which implies that the number of plus or minus sign is a value of a random variable having the binomial distribution with parameter 0.5. Okay, so we are going to do this so that we can basically use the binomial distribution to basically compute that of the p-value. Okay, so that's the intuition behind creating this median variable. So let's go back to the do file, and now once we are done with this, let's start with a sign test of the sepal length for Setosa. So let me highlight this. So I want to start with a sign test of the sepal length for Setosa. So I'm going to execute this. So I want to look at the sign test of the sepal length, and you want to see if it is equal to the median variable. If our species is equal to 1, which is basically going to pick that of the Setosa values. Okay, so let's execute this. Alright, so here we go. So if you are to compare the data point or the sepal length for Setosa to that of the median variable or the median values, we can see that we don't have any positive, which means that they are all less than the median value, which is 6 centimeters. So that's why we have negative to be 49. Okay, and we are going to use the highest number here, the highest number of plus or minus sign to compute the probability or the p-value. Okay, so we are not interested in the one-tailed test. Let's scroll down to the two-tailed test. Okay, so with a two-tailed test, we want to find the probability. Because the two-tailed test, we are going to multiply the binomial by 2, right? The probability by 2. So for a sample size of 49, right, which is basically looking at the number of plus and minus signs. Once we add them, we are getting 49. We want to find the probability that the number of negative value is at least 49, given a parameter of 0.5. And if we do that, the result is 0.000. If you have to compare this p-value to the alpha level or the threshold level of significance at 1% or 5%, it means that we are basically going to reject the null hypothesis and conclude that there's enough evidence to indicate that the median value, right, of the sepal length for Setosa is different from 6 centimeters, which is basically confirming to the inference we made under the one sample t-test. Okay, now let's check that of the sign test of the sepal length for versicolor. So let me um, highlight this. So this one is going to give us that of the sign test of the sepal length for versicolor. Okay, so let's execute this. Control D. So let me scroll up. So if you are to compare the data point, which I've already illustrated, to that of the hypothesized median value, those values of the data point that are greater than the median value are 20, and 26 of them are basically less than 6 centimeters. Okay, and 4 of them are equal to the median value, so we are going to discard them or assign 0 to them. That's why we have 4. Right, so we are going to basically add the plus and the negative ones to get a sample size. So here we are going to get a sample size of 46. Okay, so the highest number here is negative, so this is what you're going to use to compute the p-value. So let's look at the two-tailed test. So the sample size is going to be 46. I want to look at the probability that the number of negative is at least 26, given a parameter of 0.5. We are going to multiply this result by 2. So once we do that, we get a result of 0.4614. If you are to compare this to the alpha level or the threshold level of significance at 1% or 5%, it means that we are failing to reject the null hypothesis and conclude that there is insufficient evidence to indicate that the median value of the sepal length for versicolor is different from 6 centimeters. Okay, so that's the conclusion that we can draw, and this basically is similar to the result we also had under the one sample t-test. Okay, now let's check that of the sign test of the sepal length for Virginica. So let me highlight this and execute Control D. Okay, so let me scroll up. So once we compare the data point of the sepal length for Virginica to that of the hypothesized median value of 6 centimeters, those that are greater than 6 centimeters are 41, and those that are less than 6 centimeters are 6. Two of them are equal to 6 centimeters, so we discard them. So in all, we are going to get a sample size of 47. That's the number of plus sign and the number of negative signs. Okay, but in computing for the probability, we are going to use the highest number here, which is the plus signs, 41. So once we scroll down to the p-value for the two-tailed test, we have a sample size of 47. I want to find the probability that the number of plus signs is at least 41. Okay, so given a parameter of 0.5, we are going to multiply this result by 2, and we have 0.00. If you have to compare this to the alpha level of significance at 1% or 5%, it means that we are rejecting the null hypothesis and conclude that the median value, right, of the sepal length for Virginica is different from 6 centimeters, which is also similar to the result we had under the one sample t-test. Okay, So this is basically how to conduct a detailed analysis or statistical analysis for one sample data in Stata. Please, if you find value in this video tutorial, don't forget to subscribe if you have not, and also turn on the notification bell to get more updates anytime I post on this channel. Thank you for watching.